हॅलो फ्रेंड्स, आजच्या व्हिडिओमध्ये आपण क्लास 10th मॅथ्स पार्ट 2 यामध्ये असणारे वेगवेगळे जे थिरम्स आहेत वेगवेगळ्या टॉपिकमध्ये असणारे तर त्यांची प्रूफ समजून घेऊया. म्हणजे पहिल्या 3 टॉपिकमध्ये साधारणपणे ते सगळे थिरम आहेत, त्यांचा अर्थ आणि त्या आकृतीवरून त्यांची प्रूफ कशी लक्षात ठेवायची ते आपण साधारणपणे या व्हिडिओमध्ये पाहूया. त्यामध्ये जवळपास सर्व थिरम आपण ह्या व्हिडिओमध्ये समजून घेऊया, ज्याचा तुम्हाला परीक्षेमध्ये नक्की फायदा होईल. थिरम लिहित असताना सगळ्यात महत्त्वाची गोष्ट म्हणजे त्या थिरमची सगळ्यात आधी डायग्रॅम काढायची, कारण त्या डायग्रॅमवरच आधारित पुढचं सगळी प्रूफ किंवा गिवन टू प्रूव्ह कन्स्ट्रक्शन हे अवलंबून असतं. बऱ्याचदा आपण थिरम सगळ्याच्या सगळ्या बरोबर लिहितो पण डायग्रॅमच नसते. काय काय वेळेला आपल्याला ही सवय लागली असते की पाठ करून आपण ते थिरम लिहितो तसंच्या तसं, पण ते परीक्षेमध्ये तसं चालत नाही. जर डायग्रॅम नसेल आणि बाकी सगळं थिरम जरी बरोबर असेल तर त्याचे मार्क्स मिळत नाहीत आपल्याला. तर त्यामुळे लक्षात ठेवायचं की थिरम जर असेल परीक्षेमध्ये आलेला तर सुरुवात त्याची डायग्रॅमपासूनच करायची आणि मग त्याच्याखाली मग गिवन टू प्रूव्ह, त्यानंतर प्रूफ किंवा असेल तर कन्स्ट्रक्शन हे सगळं त्याच्यामध्ये आपल्याला लिहायचं असतं. तर थिरमचा अभ्यास करत असताना सगळ्यात आधी आपल्याला तो थिरम समजून घ्यावा लागतो. तो थिरम समजला तरच आपण तो लिहू शकतो. पाठ करून थिरम आपण लिहू शकत नाही. तर तो कशा पद्धतीने समजून घ्यायचं तर ते आपण ह्या व्हिडिओमध्ये पाहूया. सुरुवात करूया आपण पहिल्या थिरमला. Let's have the statement: if a line parallel to a side of a triangle intersects the remaining sides in two distinct points, then the line divides the sides in the same proportion. We have to prove this theorem, so for that we need a diagram. Let us have a triangle ABC where line L intersects side AB and side AC at points P and Q respectively. So this is the figure given. From this we are given that in triangle ABC, line L is parallel to line BC and line L intersects sides AB and sides AC in points P and Q respectively. This is the given. From this we have to prove that this line L divides those two lines AB and AC in the same proportion. That is, if we take a ratio of AP and PB, it must be equal to the ratio of AQ and QC. So that is, to prove is AP divided by PB is equal to AQ divided by QC. So to prove this we need one construction, that is we have to draw segment PC and segment BQ. So by doing this construction we are going to prove this theorem. So the firstly, by doing the construction we have got two triangles, triangle APQ and triangle PQB. For triangle APQ and triangle PQB, as we can see, they have the same heights. That's why the ratio of their areas must be equal to the corresponding bases. So for triangle APQ, the base, if we consider AP, for triangle PQB, the base will be PB. So ratio of their areas, that is area of triangle APQ divided by area of triangle PQB, that is equal to AP divided by PB, which are bases of these two triangles. So we call this as equation number 1. Similarly, we have another pair of triangles, that is triangle APQ and triangle PQC. So again, as we can see, these two triangles have equal heights. That's why the ratio of their areas must be equal to the corresponding bases. For triangle APQ, base is AQ, and triangle PQC, the base is QC. So the ratio of their areas must be equal to AQ divided by QC, as we have written here. Area of triangle APQ divided by area of triangle PQC is equal to AQ divided by QC. We will call this as equation number 2. Consider triangle PQB and triangle PQC. So these two triangles are situated in between two parallel lines, as line L is given to be parallel to line BC. That's why in between these two parallel lines there are two triangles situated. So as these are the two triangles situated in between two parallel lines, they have equal bases and equal heights. That's why by the property these two triangles have equal areas. That is, area of triangle PQB is equal to area of triangle PQC. We will call this as equation number 3. Now if we compare equation 1, 2 and 3, from these we can have, as you can see, the left hand sides of equation 1 and 2 are equal. That is, area of triangle APQ divided by area of triangle PQB is equal to area of triangle APQ divided by area of triangle PQC. As in the numerator of the left hand sides of equation 1 and 2 have the single triangle, that is triangle APQ, and in the denominator we have triangle area of triangle PQB and area of triangle PQC, which we have proved that these areas of these two triangles are equal in equation number 3. That's why the left hand sides of equation 1 and 2 are equal. That is, area of triangle APQ divided by area of triangle PQB is equal to area of triangle APQ divided by area of triangle PQC. And this is from equation 1, 2 and 3. Now as left hand sides of equation 1 and 2 are equal, so the right hand sides must be, right hand side of equation 1 is AP divided by PB and the right hand side of equation 2 is AQ divided by QC. So as the left hand sides are equal, right hand sides must be equal. So from equation 1, 2 and 3 we have AP divided by PB is equal to AQ divided by QC. That is from equation 1 and 2. That is, we have to prove that is AP by PB is equal to AQ by QC. And the next theorem is again from the same topic, that's similarity. And the theorem is theorem of areas of a similar triangle. So first of all, let us have the statement of the theorem. When two triangles are similar, then the ratio of areas of those triangles is equal to the ratio of the squares of their corresponding sides. So this is the statement of the theorem. Now let's illustrate this theorem with the help of a diagram. So these are the two triangles given, triangle ABC and triangle PQR. So these two triangles are given to be similar, and for those two triangles the given would be triangle ABC is similar to triangle PQR, which is given, where AD is perpendicular to BC. So for triangle ABC, AD is the height and BC is the base. In the same way, PSC is perpendicular to QR, that means PS is the height and QR is the base for triangle PQR. So this is given, and from this we have to prove that if we take the ratio of areas of these two triangles, that is area of triangle ABC divided by area of triangle PQR, it must be equal to, it is given that the ratio of squares of their corresponding sides. So the first ratio is AB divided by PQ, and we have to make it square. That's why it is AB square by PQ square. So this is the first ratio of the corresponding sides. As it is a triangle, it must have three sides. That means it must have three ratios. The second ratio is BC square divided by QR square, because BC and QR are the corresponding sides, and the remaining ratio is AC square by PR square. So this is, we have to prove area of triangle ABC divided by area of triangle PQR is equal to AB square by PQ square is equal to BC square by QR square is equal to AC square by PR square. Now let's have the proof of the theorem. So we'll start with the given thing. That means as these two triangles are given, AD is perpendicular to BC and PS is perpendicular to QR, and that's why we have another pair of triangles, that is triangle ADP and triangle PSQ, or in other words we can name these triangles as triangle ABD and triangle PQS. So these two triangles, we have to show that these two triangles are similar. So the first element is angle B is congruent to angle Q. As triangle ABC is similar to triangle PQR and angle B and angle Q are the corresponding angles, so they must be congruent. So that's why the reason is given. So for these two triangles, angle B is congruent to angle Q. The second element is angle ADB. This angle must be of measure 90 degree because AD is perpendicular to BC. In the same way, angle PSQ is also 90 degrees. So these two angles must be congruent as each has a measure of 90 degrees. So by having these two elements, we can have these two triangles similar by AA test. That's why triangle ABD is similar to triangle PQS by AA test. And we know one property of similar triangles, that if two triangles are similar, then the corresponding angles are congruent and corresponding sides are in proportion. So we'll take here AD divided by PS. So AD means first and the third vertex. Its corresponding side is PS. That's why the first ratio is AD divided by PS. That must be equal to AB divided by PQ. So to take AB, first and the second vertex we have to take, and the corresponding side would be PQ. So the second ratio is AB divided by PQ. And we can take this because these are the corresponding sides of similar triangles. So that must be the reason, and we'll call this as equation number 1. Now, it is given that triangle ABC is similar to triangle PQR. So if these two triangles are similar, then their corresponding sides must be also in proportion. So if we take side AB, its corresponding side would be PQ. So AB divided by PQ is equal to BC divided by QR. Again, the reason is same here. Corresponding sides of similar triangles. We'll call this as equation number 2. Now we have to take the ratio of areas of these two triangles. So if we take the ratio of areas of these two triangles, that is area of triangle ABC divided by area of triangle PQR, the basic formula is, if two triangles are there and if we have to take the ratio of their areas, the formula is the ratio of corresponding bases and heights of those two triangles. So area of triangle ABC divided by area of triangle PQR is equal to BC into AD, as BC is the base for first triangle and AD is the height, divided by QR into PS, as QR is the base and PS is the height for the second triangle. So it can be split as BC by QR into AD divided by PS. Now to the next step, the first ratio would be as it is BC by QR into, instead of AD by PS we can write BC by QR. Now why is this so? Because of equation number 1 and equation number 2. Let's see how it is. AD divided by PS is equal to AB divided by PQ, and AB divided by PQ is equal to BC divided by QR. That's why we can say that AD divided by PS must be equal to BC divided by QR. So from equation 1 and 2, instead of AD divided by PS, we can write BC divided by QR. And to the next step now, we have BC divided by QR into BC divided by QR. That's equals to BC square divided by QR square. Now this is area of triangle ABC divided by area of triangle PQR is equal to BC square by QR square. So as we have proved this theorem for one corresponding side of a triangle, in the same way we can prove it for remaining two also, and hence we get the result as area of triangle ABC divided by area of triangle PQR is equal to AB square by PQ square is equal to BC square by QR square is equal to AC square by PR square. So this is the theorem of areas of similar triangles. The next theorem is from the topic Pythagoras theorem, that is the theorem of geometric mean. Before we know what is the theorem of geometric mean, first of all we must know the concept of geometric mean. So let us understand that firstly. Suppose there are three numbers A, B and C given, in which if it is given that B square is equal to A into C, that is the middle term square is equal to product of the remaining two terms, then in this case we say that B is the geometric mean of A and C. So we have to use this principle in a right angle triangle, in which we have to prove the theorem of geometric mean. So let us have the theorem of geometric mean. The statement is, in a right angle triangle, the perpendicular segment to the hypotenuse from opposite vertex is the geometric mean of the segments into which the hypotenuse is divided. To understand this, we must have a diagram. Consider triangle PQR, which is a right angle triangle given, where angle Q is a right angle. In this triangle, we have to prove that a perpendicular segment to the hypotenuse. So in this diagram, the perpendicular segment to the hypotenuse is QS, as QS is perpendicular to PR, is the geometric mean of the segments into which the hypotenuse is divided. So we have to prove that QS is the geometric mean of segments PS and segment SR, as QS divides hypotenuse into these two segments. That's why we have to prove that QS is the geometric mean of PS and SR. For this one, it is given that in a right angle triangle PQR, QS is perpendicular to hypotenuse PR. So as QS is a perpendicular to hypotenuse PR, we have the property of similarity of right angles. That is, if in a right angle triangle a perpendicular drawn to the hypotenuse from opposite vertex, we got three triangles. Those three triangles are similar to each other. So by that we have triangle QSR is similar to triangle PSQ. So these two triangles are similar for this given correspondence, that is PSQ is similar to triangle QSR. So to remember this one, we have to start with P from P to S and then S to Q, so as to get a triangle PSQ. And again we have to start with Q to S, that is QS, and from S to R to get the second triangle QSR. So here triangle PSQ and triangle QSR, these are the two triangles we have to take. By the similarity of right angles, these two triangles are similar. So we have to remember these two triangles for this given correspondence. So if these two triangles are similar, then we have the property of sides of similar triangles, that is sides of similar triangles are in proportion. So if we take the side QS, its corresponding side is PS. So we have QS divided by PS is equal to SR, its corresponding side is SQ, that is equal to SR divided by SQ. So we can rearrange these terms as QS divided by PS is equal to SR divided by QS. Now if we cross multiply, we get QS into QS, that's QS square, is equal to PS into SR. So what does this suggest? That is QS square is equal to PS into SR. That means the square of QS is equal to product of PS and SR. That is QS is the geometric mean of PS and SR. That is, we wanted to prove segment QS is the geometric mean of segment PS and segment SR. So this is the geometric mean theorem. Now the next theorem is the theorem of Pythagoras from the second topic. Before this, we have studied what is the Pythagoras theorem. In this session we are going to prove the Pythagoras theorem. So let us have the statement of the theorem. In a right angle triangle, the squares of the hypotenuse is equal to the sum of the squares of remaining two sides. So as we know, this is the Pythagoras theorem. To prove this, we need a diagram. So let us have triangle ABC, which is a right angle triangle given. So given will be in triangle ABC, it is given that angle B is a right angle, that is angle ABC is equal to 90 degree. So in this triangle we have to prove that square of hypotenuse is equal to the sum of the squares of remaining two sides. So for this triangle, side opposite to 90 degree is the hypotenuse. So AC is the hypotenuse. So we have to prove that AC square is equal to remaining two sides are AB and BC. So we have to prove AC square is equal to AB square plus BC square. Now to prove this, we have to do one construction. We have to draw a perpendicular BD from vertex B to the hypotenuse AC. And by doing this, we have got A, D and C are collinear. Let's start with the proof. So in a right angle triangle, we have constructed segment BD perpendicular to AC. So by doing this, we have got three right angle triangles. So here we have to use the property of similarity of right angle triangles. So if in a right angle triangle, if we draw a perpendicular on the hypotenuse from its opposite vertex, the three right angle triangles so formed are similar to each other. So this is the property of similarity of right angle triangles. By that we had triangle ABC is similar to triangle ADB is similar to triangle BDC. So we have to take these three triangles which are similar for this given correspondence only. That is, we have to take triangle ABC is similar to triangle ADB, which is similar to triangle BDC. So for this correspondence, these three triangles are similar. Now let us consider first two of them, that is triangle ABC is similar to triangle ADB. Now as these two triangles are similar, their corresponding sides must be in proportion. So if we take side AB, its corresponding side is AD. So we have AB divided by AD is equal to, We take first and the third vertex, that is AC, then its corresponding side is AB. So we have AC divided by AB. And this is because these are the corresponding sides, and the corresponding sides of similar triangles are in proportion. That's why we have AB divided by AD is equal to AC divided by AB. Now if we cross multiply, we get AB into AB, that's AB square, is equal to AD into AC. We call this as equation number 1. In the same way, now we consider the first and the third triangle similar, that is triangle ABC is similar to triangle BDC. Here also the corresponding sides must be in proportion. So if we take BC, its corresponding side is DC is equal to AC, its corresponding side is BC. So we have BC divided by DC is equal to AC divided by BC. Again the reason is corresponding sides. Here also if we cross multiply BC into BC, we get BC square is equal to DC into AC, equation number 2. We compare what is to prove. We have to prove that on the right hand side AB square plus BC square. So in equation number 1 and 2, as we can see, the left hand sides are AB square and BC square. So here we should take its sum. That's why one operation we must do on these two equations is addition. So we must add equation 1 and equation 2. So adding equation 1 and 2, we have to add left hand sides to the left hand side, that is AB square plus BC square, which are the left hand sides of equation 1 and 2. So we have AB square plus BC square is equal to, now we have to add the right hand side to the right hand side of equation 1 and 2. So the right hand side of equation 1 is AD into AC plus right hand side of equation 2 is DC into AC, that is DC into AC, which is equal to, from these two terms we have AC as a common. So we take AC as a common. So in bracket we have AD plus DC remaining, that is equal to AC into, as we can see in the diagram, what is AD plus DC? As A, D and C are collinear points, AD plus DC we get AC. So instead of AD plus DC we can write AC, so as to have AC into AC, that is equal to AC square. So we get here AB square plus BC square is equal to AC square. By rearranging it, we get AC square is equal to AB square plus BC square. So that is we wanted to prove. For in a right angle triangle, the hypotenuse square is equal to the sum of the squares of remaining two sides. This is the Pythagoras theorem. Now the next very simple and interesting theorem from the topic circle, that is the theorem of cyclic quadrilateral. First of all, let us see what is cyclic quadrilateral. Suppose there is one circle given, and on that circle if we have 4 points, that is A, B, C, D, and if we draw a quadrilateral A, B, C, D, we can observe that all the vertices of this quadrilateral are on the circle. So such a quadrilateral is called as a cyclic quadrilateral. We can define cyclic quadrilateral as, if all the vertices of a quadrilateral lie on the same circle, then it is called as a cyclic quadrilateral. Now we have one property about this cyclic quadrilateral, which is called as a theorem of a cyclic quadrilateral. First of all, let us see what is the statement. The statement is, opposite angles of cyclic quadrilateral are supplementary. We are going to prove this one. For that we need a diagram. So let us have a diagram in which quadrilateral A, B, C, D is given, which is a cyclic quadrilateral. We are going to prove this theorem in the form of one activity. So here we have to write the given and to prove. So from this statement and from this diagram we have to fill this. Given is quadrilateral dot dot is a cyclic. So as we can observe here in diagram, quadrilateral ABCD is given. So quadrilateral ABCD is a cyclic quadrilateral which is given. To prove is angle B plus angle D. So as we can see, angle B and angle D are opposite angles of cyclic quadrilateral, and we have to prove that they are supplementary. That means sum of their measures must be 180 degree. In the same way, there is another pair of opposite angles, that is angle A and angle C. So here the next bracket must be angle A plus angle C is equal to 180 degree. These two statements we are going to prove. For that one, let us start with the proof. As we can observe, arc ABC in the diagram, arc ABC is intercepted by angle ADC. So as we can observe, the sides of angle ADC passes through two endpoints of this arc. That's why arc ABC is intercepted by angle ADC. So by using inscribed angle theorem, we can write measure of inscribed angle is half of measure of its intercepted arc. That means angle ADC is equal to half of measure of arc ABC. Similarly, there is another angle ABC, which is inscribed angle, and it intercepts arc ADC. That's why here we can write angle ABC is also inscribed angle and it intercepts arc ADC. So same theorem should be applied here to write angle ABC is equal to half of measure of arc ADC. We will call this as equation number 2 and the first one as equation number 1. Now if we add these two equations, equation 1 and equation 2, we have to add left hand side to the left hand side. So the left hand side of equation 1 is measure of angle ADC plus the left hand side of equation 2 is measure of angle ABC. That is equal to, now the right hand side of equation 1 is 1 half of measure of arc ABC plus right hand side of equation 2 is 1 half measure of arc ADC. Now from both of these two terms, we can take 1 half common. So in bracket, we would have measure of arc ABC plus measure arc ADC. So if we can see in the diagram, what is measure of arc ABC and measure of arc ADC. If we add these two arcs, we get a circle. And we know that the measure of a circle is 360 degree. That's why we get 1 half into 360 as measure of arc ABC plus measure of arc ADC, it is 360 degree. Because arc ABC and arc ADC constitute a complete circle. Now if we divide 360 by 2, we get 180 degree. That is measure of angle ADC plus measure of angle ABC is equal to 180 degree. In short, may be written as angle A plus angle C is equal to 180 degree. This is the second statement we have proved here. In the same way, we can prove angle B plus angle D is equal to 180 degree. This is the proof of the theorem of cyclic quadrilateral. That is, opposite angles of a cyclic quadrilateral are supplementary. The next theorem is inscribed angle theorem. The statement of the theorem is the measure of an inscribed angle is half of the measure of arc intercepted by it. To prove this theorem, we need a diagram. So let's start with a diagram. So there is a circle with center O and it is given that in a diagram angle BAC is inscribed in arc BAC and arc BDC is intercepted by angle BAC. So this is the given. From this one we have to prove that measure of inscribed angle, that is measure of angle BAC, is half of measure of arc BDC, because if we draw here segment BO, then angle BOC will be the central angle, and we know that measure of the corresponding arc is equal to the measure of the central angle. So whatever will be the measure of angle BOC, that must be the measure of arc BDC. So we have to prove here that measure of angle BAC is equal to half of measure of arc BDC, which is intercepted in angle BAC. So that is we have to prove. For this one we need to do one construction. We have to draw ray AO such that it intersects a circle at point E, and also we have to join points O and C so as to have the radius OC. So by doing this construction, now we'll start the proof of this theorem. By doing this construction, we get one triangle AOC. For this triangle, we have side OA is congruent to side OC, as these are the radii of the same circle. And we know that if in a triangle two sides are congruent, then angles opposite to them are also congruent. So angle OAC and angle OCA are the two angles opposite to side OA and side OC. That's why they are also congruent, and this is by theorem of isosceles triangle. Let the measure of these two angles be x. That is, angle OAC is equal to angle OC is equal to x. We will call this as equation number 1. Now, if we consider angle EOC, this is the exterior angle of triangle AOC. By exterior angle theorem, we know that the measure of exterior angle is equal to sum of its remote interior angles. Means angle EOC is equal to measure of angle OAC plus angle OCA, as these two are the remote interior angles of angle AOC. That's why we have written here angle EOC is equal to angle OAC plus angle OCA. And we have supposed the measures of these two angles to be x. That's why we get here x degree plus x degree, that is equal to 2x degree. So measure of angle EOC is equal to 2x degree. Now, angle EOC is the central angle. We know that measure of an arc is equal to the measure of the corresponding central angle. That's why measure of arc EC is equal to 2x degree, because corresponding central angle of arc EC is angle EOC, and we have found measure of angle EOC as 2x degree. That's why measure of arc EC is also 2x degree. This is by definition of measure of an arc. Now, if we compare equation 1 and 2, we have angle OAC, as we can see in the diagram, angle OAC. We can also call angle OAC as angle EAC. It is equal to half of measure of arc EC, as measure of angle EAC is x degree and measure of arc EC is 2x degree. That means measure of angle EAC is equal to half of measure of arc EC. This is equation number 3. In the same way, we can prove this for angle EAB. That means measure of angle EAB must be also equal to half of the measure of arc BE. That is equation number 4. Now, if we add equation 3 and 4, we can add left hand side to the left hand side to have angle EAC plus angle EAB, that is equal to the right hand sides of equation 3 and 4 are 1/2 measure of arc EC plus 1/2 measure of arc BE. If we take 1/2 common in bracket, we have measure of arc EC plus measure of arc B, and on the left hand side we have angle EAC plus angle EAB. So if we add these two angles EAC and EAB, we get angle BAC. So on the left hand side we have angle BAC is equal to half of measure of arc EC plus measure of arc BE. If we add these two arcs, we get arc BDC. That's why we replace here measure of arc EC plus measure of arc BE by measure of arc BEC. So we have 1/2 measure of arc BEC, and measure of arc BEC can be also named as measure of arc BDC. So we get here angle BAC is equal to half of measure of arc BDC. That is we wanted to prove. So this is inside angle theorem. Now the next concept from the topic circle. The concept is theorem of angle between tangent and secant. So first of all, let us have the statement of the theorem. If an angle has its vertex on the circle, its one side touches the circle and the other intersect the circle in one more point, then the measure of the angle is half of the measure of its intercepted arc. So let us start to understand this theorem by using the diagram. Suppose if we have a circle where angle ABC is given. Now side BC of angle ABC touches the circle at point B, that is B is point of contact, and the other side of the angle is AB, which intersects the circle at point A. In this diagram, the second side of angle ABC passes through the center of the circle. So this is the first condition that we may get. We have another possibility that if there is a circle given and there is an angle ABC, the first side touches the circle at point B, and this time the second side of an angle ABC intersects the circle at point A, which makes an acute angle. So this possibility also can be there. And we have another possibility that the angle which is an obtuse angle. So here in the third diagram, the second side of angle ABC intersects the circle at point A, which makes an obtuse angle. Now for all these three diagrams, we are given that for angle ABC, the vertex B of angle ABC, which lies on the circle. Now for all these diagrams, side BC touches the circle at point B and side BA intersects the circle at point A. In this case, arc ADB is intercepted by angle ABC. So as we can see, for all these diagrams, arc ADB is intercepted by angle ABC, and for third diagram also, arc ADB is intercepted by angle ABC. Now if this is the case, then measure of angle ABC must be half of the intercepted arc, as the statement suggests that. Then the measure of angle is half of its intercepted arc. That means measure of angle ABC is equal to half of measure of arc ADB. So this theorem is known as theorem of angle between tangent and secant, as one side of angle touches the circle, that's why it is a tangent, and other side intersects the circle, that's why it is a secant. So the theorem is called as the theorem of angle between tangent and secant. Now we can see this theorem using another angle. That's why we have alternate statement of this theorem. Suppose this circle is given where angle ABC, for this angle side BC touches the circle at point B and AB intersects the circle at point A. In this case, by using the previous theorem, we can write measure of angle ABC must be half of the intercepted arc, that is half of measure of arc ADB. So this can be written by using the previous theorem. Now if you consider angle ATB, where T is any other point which is taken on the circle, and we have joined here AT and TB. For this angle ATB, arc ADB is also intercepted by the same angle, that is arc ADB is intercepted by angle ATB. Now by inscribed angle theorem, we have measure of angle ATB must be half of measure of arc ADB. So that can be written as angle ATB is equal to half of measure of arc ADB. So from these two we can conclude that measure of angle ABC is half of arc ADB, and also measure of angle ATB is half of arc ADB. That's why measure of angle ABC is equal to measure of angle ATB. So this is the alternate statement of the above theorem, that an angle between a tangent of a circle and a chord drawn from the point of contact is congruent to angle inscribed in the arc opposite to the arc intercepted by that angle. Now let us study another theorem, tangent secant segments theorem. Let us have its statement. For this diagram, if point E is in the exterior of a circle, the secant through point E intersects the circle at point A and B respectively, and a tangent which is drawn through point E which touches the circle at point T, that's given. So if it is the case, then we have EA into EB, that is equal to ET square. As we can see in the diagram, EA into EB, that must be equal to ET square. So we have to prove this. For that we have to do one construction. We have to draw segment AT and segment TB. Now by doing this construction, we have got two triangles, triangle EAT and triangle ETB. Now for these two triangles, we have angle AET which is congruent to angle TEB, because this is the common angle for both of these two triangles. That's why these two angles are congruent, because of common angle. Second component is angle ETA, this one is congruent to angle EBT, and this is because a tangent secant theorem. Now for these two triangles, two angles of first triangle are congruent to two corresponding angles of the second one. That's why these two triangles must be similar by A test. So triangle EAT is similar to triangle ETB. And we know that if two triangles are similar, then their corresponding sides are in proportion. So if we take side ET, its corresponding side will be EB. So ET divided by EB is equal to EA, its corresponding side is ET, is EA divided by ET. If we cross multiply, we get ET into ET, that's ET square, is equal to EA into EB. So we get EA into EB is equal to ET square. That is we wanted to prove. So this theorem is known as tangent secant segments theorem. Theorem of internal division of chords and theorem of external division of chords. So start with the first theorem, theorem of internal division of chords. Let us have its statement. Suppose two chords of a circle intersect each other in the interior of a circle, then the product of the lengths of two segments of one chord is equal to the product of lengths of two segments of the other chord. Now let us try to illustrate this by using a diagram. Suppose there is one circle with center P, and as we can see, chord AB and chord CD are intersecting at point E, which is inside the circle. So if it is the case, then we have to prove that the product of lengths of two segments of one chord, that means for chord AB, two segments are AE and BE, which are made due to the point of intersection E. So if we take a product of AE and BE, it must be equal to the product of length of two segments of the other chord. So two segments of the other chord are CE and ED. So if we take a product of CE and ED, it must be equal to AE into EB, that we have to prove. So for this diagram given is chord AB and chord CD of a circle with center P intersect at point E. That's given. And from that we have to prove that AE into EB is equal to CE into ED. So again, as we can see in the diagram, AE into B, that must be equal to CE into ED. Now to prove this, we have to do one construction. We have to join points A and C and points B and D. So that is the construction, cross segment AC and segment DB. By doing this construction, we have got two triangles, triangle CAE and triangle BDE. We have to show that these two triangles are similar. If we can show these two triangles are similar, then we'll get the result. Now for these two triangles, we have the first pair of congruent components, that is angle AEC is congruent to angle DEB. As these two angles are vertically opposite angles, they must be congruent. Now we have another component, that is angle CAE is congruent to angle BDE, as both of these two angles are inscribed in the same arc, that is angle CAE and angle BDE are inscribed in arc CAB. And we know that if there are two angles which are inscribed in the same arc, those must be congruent. That's why these two angles are congruent, as these are angles inscribed in the same arc. Now we have two pairs of angles of these two triangles which are congruent. That's why these two triangles must be similar by AA test. That is angle CAE is similar to triangle BDE by AA test. As these two triangles are similar, their corresponding sides must be in proportion. Now we have to select sides that we have to prove. That means we have to take side AE. So if we consider the second and third vertex of the first triangle, then we get side AE. Its corresponding side is DE. So we have AE divided by DE, that is equal to, we need here again CE. So we'll take the first and the third vertex CE. Its corresponding side is BE. So that is equal to CE divided by BE, as these are corresponding sides of similar triangles. Now if we cross multiply, we get AE into EB, that is equal to CE into ED. That is, we wanted to prove AE into EB is equal to CE into ED. This theorem is called as theorem of internal division of chords. So let us revise this one. Suppose this is a circle where chord AB and chord CD intersect each other at point E, which is inside the circle. Then in this case, we have AE into EB, that is equal to CE into ED. and this property is known as theorem of chords intersecting inside the circle. Let us have the next theorem, theorem of external division of chords. So let us have the statement of the theorem. Let us consider the diagram given. For this diagram, if seconds containing chord AB and chord CD of a circle intersect outside the circle at point E, then in this case we have to prove that AE into EB, that is equal to CE into ED. So we are going to prove this one. For that one, let us have one construction. We have to draw segment AD and segment BC. So by doing this construction, we have got two triangles. We have to consider triangle ADE and triangle CBE. For these two triangles, angle AED is congruent to one angle which is a common angle. So it must be angle AED is congruent to angle CEB, as this angle is there in both of these two triangles. That's why these two angles are congruent, because this is a common angle. Then angle DAE is congruent to angle BCE. So it's given, we have to write the reason. So the reason is, these are the two angles which are inscribed in the same arc. So as we can observe, both of these two angles, angle DAE and angle BCE, are inscribed in arc ABC. That's why these two angles are congruent. Therefore, these two triangles, triangle ADE and triangle CBE, must be similar by AA test. So triangle ADE is similar to triangle CBE by AA test. As these two triangles are similar, the corresponding sides must be in proportion. So if we take AE, its corresponding side must be CE. So we should write AE divided by CE is equal to, if we take side ED, that is third and the second vertex of first triangle, then its corresponding side is EB, and the reason is corresponding sides of similar triangles. If we cross multiply, we get AE into EB, that is equal to CE into ED. So that is, we wanted to prove AE into EB, that is equal to CE into ED. So this is the theorem which is called as theorem of external division of chords. That means if there are two chords given for a circle, if we draw seconds containing those chords, the seconds intersect each other at the point which is outside the circle. So if this is the case, then we have this product AE into B, that is equal to CE into D. So let us revise this one. Suppose this is a circle where chord AB and chord CD intersect each other at point E, which is inside the circle. Then in this case, we have AE into EB, that is equal to CE into ED, and this property is known as theorem of chords intersecting inside the circle. Now if we consider another diagram, so this is the circle where chords AB and chord CD intersect each other at point E, but now this time point E is in the exterior of a circle. Now if this is the case, then also the product AE and EB, that is equal to CE and ED. This property is known as theorem of chords intersecting outside the circle. Some corollaries based on inscribed angle theorem. Earlier we have studied what is the inscribed angle theorem. Also we have studied the proof of it. The link is given in the description. You can watch that video. Today we are going to learn some properties which are based on inscribed angle theorem. To start with the first property. So for the first property, first let us consider this diagram. So as we can see in the diagram, there are two angles given, angle PQR and angle PSR. So if we consider angle PQR, it is inscribed in arc PQR, and the second angle PSR, it is also inscribed in the same arc, that is arc PQR. So if these two arcs are inscribed in the same arc, the first corollary based on the inscribed angle theorem is that if there are two angles inscribed in the same arc, then those two angles are congruent. Let us have the verification of it. We know the inscribed angle theorem that measure of inscribed angle is half of measure of an intercepted arc. So as we can see here, arc PTR is intercepted by angle PQR. So from this one, by using inscribed angle theorem, we have angle PQR is equal to half of measure of arc PTR, as arc PTR is intercepted by angle PQR. So this is called as equation number 1. The same way, arc PTR is the only arc which is again intercepted by the second angle, this angle PSR. So here also by inscribed angle theorem, we have angle PSR is equal to half of measure of arc PTR, because by inscribed angle theorem, the measure of inscribed angle is half of measure of intercepted arc. So we'll call this as equation number 2. So if we compare equation 1 and 2, we can see the right hand sides of these two equations are equal. So the left hand sides must be. That means angle PQR is equal to angle PSR. And as you can see in the diagram, angle PQR and angle PSR are inscribed in the same arc. From this one, we can conclude that angle PQR and angle PSR are inscribed in arc PQR, that is, they are inscribed in the same arc. That's why they are congruent. So the corollary is angles inscribed in the same arc are congruent. So this is the first corollary based on inscribed angle theorem. Now let us learn the second corollary. For this one, again consider a circle where AC is the diameter, M is the center of the circle, and angle ABC is inscribed in arc ABC. And as we can see here, arc ABC is nothing but a semicircle. So we have to find what is the relation between angle BAC and this semicircle. So as we can see, angle ABC is inscribed in arc ABC, and arc AXC is intercepted by angle ABC. So as arc AXC is inside the angle ABC, that's why it is intercepted by angle ABC. So we have, by inscribed angle theorem, measure of angle ABC is equal to half of measure of arc AXC. But here, as we know, arc AXC is nothing but a semicircle, and the measure of a semicircle is 180 degree. That's why angle ABC is equal to half of 180 degree, as we have replaced here measure of arc AXC by 180 degree. If we divide by 2, we'll get 90 degree, that is measure of angle ABC is equal to 90 degree. So here angle ABC is inscribed in the semicircle and its measure is 90 degree. So from this we can conclude that angle inscribed in a semicircle is a right angle. So this is the second corollary based on inscribed angle theorem. So two corollaries which we have studied based on inscribed angle theorem. The first of that is angles inscribed in the same arc are congruent, and the second corollary is angle inscribed in a semicircle is a right angle. Let us try to understand tangent segment theorem. Before we know what is tangent segment theorem, we must know what is a tangent of a circle. Let's learn what is a tangent of a circle. For that, let us consider one circle in a plane. In the same plane, suppose there is one line given. Now, if the line touches the circle at only one point, it is called as the tangent of a circle, and the point at which it touches the circle is called as a point of contact. So here, as we can see, line L touches the circle at point A. That's why line L is called as a tangent of a circle, and point A is the point of contact. So by knowing this, the definition of a tangent of a circle, let's move to our theorem. Tangent segments drawn from an external point to a circle are congruent. We need to prove this. For this one, we need a diagram. So let us consider one circle given with center A. Point D is in the exterior of the circle, and from point D, line DP and line DQ are the two tangents drawn. So for this one, we are given that in a circle with center A, line DP and line DQ are two tangents drawn to a circle which touches the circle at point P, and point Q respectively. Now we need to prove that the tangent segments drawn from external point are congruent. So as we can see here, DP and line DQ are the two tangents. Here we have one term, tangent segment. What is tangent segment? The limited portion of a tangent is called as a tangent segment. So as we can see in the diagram, segment DP is the limited part of line DP. That's why segment DP is called as a tangent segment. In the same way, segment DQ is also a tangent segment. So we have to prove that these two tangent segments are congruent. That is, to prove is segment DP is congruent to segment DQ. Now to prove this, we need one construction. We have to draw segment PA and segment QA, which are the radii of the same circle. Now by doing this construction, we have got two triangles, triangle APD and triangle AQD, from which we have to start the proof. That is, to start with, in triangle PAD and triangle QAD, which are formed due to this construction, we are trying to prove that these two triangles are congruent. So the first constituent element of these two triangles is segment PA is congruent to segment QA. So as we can see, these are the radii of the same circle. They must be congruent. So segment PA is congruent to segment QA as these are the radii of the same circle. So the second element is segment AD is congruent to segment AD as segment AD is the common side for both of these two triangles. And the reason is common side. So these are the two constituent elements of these two triangles which are congruent. Now as measure of angle APD and measure of angle AQD is 90 degree each because of the tangent theorem. As we know, DP is the tangent and PA is the radius, and we know that tangent is perpendicular to the radius. So angle between them, that is angle APD, is a right angle. That's why angle APD is equal to 90 degree. In the same way, angle AQD is also 90 degree. So as these two angles are of measure 90 degree each, these two triangles must be right angle triangle. And in a right angle triangle, we have proved here that hypotenuse and one side of one triangle is congruent to hypotenuse and the corresponding side of the other triangle. That's why these two triangles are congruent by hypotenuse side test. That's why triangle PAD is congruent to triangle QAD by hypotenuse side test. And as these two triangles are congruent, their corresponding sides must be also congruent. If we take side DP, its corresponding side is DQ. So segment DP is congruent to segment DQ. Reason is corresponding sides of congruent triangles. That is, we wanted to prove segment DP is congruent to segment DQ as segment DP and segment DQ are the tangent segments drawn to a circle from an external point. That is, we have to prove that the tangent segments drawn from an external point to a circle are congruent. Hello friends, today let's solve one problem based on one concept from the topic circle, class 10, that is the theorem of cyclic quadrilateral. So there is a theorem of cyclic quadrilateral. So we are going to solve one problem which is based on theorem of cyclic quadrilateral. So let's have the question. Quadrilateral MRPN is a cyclic quadrilateral. It's given. The measure of angle R is given in terms of the variable x, that is 5x minus 13 degree. Measure of angle N is 4x plus 4 degree. And from this information we have to find the measures of angle R and angle N. So to solve this question, first of all we should have the diagram. So let us have the circle. Now as quadrilateral MRPN is a cyclic quadrilateral given, that means all these four vertices, that is point M, point R, point P and point N, must be on the circle as it is a cyclic quadrilateral. Because according to the definition of cyclic quadrilateral, if a quadrilateral is to be a cyclic quadrilateral, all the vertices of that quadrilateral must lie on the circle. So if we join these vertices, we get a quadrilateral which is a cyclic quadrilateral. So if we join M and R, then R and P, N and P, and finally M and N. So this is the cyclic quadrilateral. Now measure of angle R is given to be 5x minus 13 degree, and measure of angle N is 4x plus 4 degree. So these are the opposite angles of a cyclic quadrilateral, and we have one property of opposite angles of a cyclic quadrilateral. The opposite angles of a cyclic quadrilateral are supplementary, so we are going to use that property. So we'll start with the given, that is quadrilateral MRPN is a cyclic quadrilateral. So we have the theorem of cyclic quadrilateral. So by that theorem we have the theorem of cyclic quadrilateral. The opposite angles of a cyclic quadrilateral are supplementary. So angle R and angle N, this is the pair of opposite angles of cyclic quadrilateral MRPN. So they must be supplementary. And supplementary means if we add these two angles, angle R plus angle N, sum of their measures must be 180 degree. Now we have the measure of angle R, that is 5x minus 13, plus we have the measure of angle N, that is 4x plus 4 degree, and this is equal to 180 degree on the right hand side as it is. Now if we add 5x and 4x, it is 9x, minus 13 plus 4, it is minus 9, is equal to 180 on the right hand side. So 9x is equal to 180 minus 9, going to the right hand side it will become plus 9. So we get 9x is equal to 180 plus 9, that's 189. We have to find the value of x. So that's why we'll transfer 9 to the right hand side so as to have in the denominator. Now if we divide 189 by 9, we get 9 2s are 18 and 9 1s are 9. So x is equal to 21. So this is the value of x. We don't want the value of x, we want the measures of angle R and angle N. So we have measure of angle R in terms of the variable x as 5x minus 13 degree. So 5 into value of x we have just found to be 21. So it should be bracket, it should be in bracket minus 13. So 25 into 5, it's 105 minus 13, that is equal to 92 degree. So this is the measure of angle R. In the same way we can find the measure of angle N also. So to find that we have again angle N, it is equal to 4x plus 4 degree. So 4x plus 4 degree. So instead of x we should write here 21. So 4 into 21 plus 4. So 21 into 4, that's 84 plus 4, and 84 plus 4, that's 88 degree. So these are the measures of angle R and angle N. That is, the measure of angle R is 92 degree and the measure of angle N is 88 degree. So this is how we can solve problems based on the theorem of cyclic quadrilateral.